Okay, let's dig into this phenomenon more by having the following. Right? So let C sub 1 and C sub 2. We could use capital C and capital D. We're just using C1 and C2. Let these be two paths which have the same initial point and the same final point. That's all that has to be true about these two paths. So just to draw a picture, okay, we'll get some axes there first. Maybe starting here, ending there, you could have C1 be a very, very nice, really basic path, just a straight line segment. And then C2, you could just make that. C2 travels like this, and it's just a much more wacky path. Now here's the thing. Though the integral over C1 of a vector field dot dr and integral over C2 of vector field dot dr. So for the same vector field here and here, okay, though these two integrals are usually different, okay, you should be expecting different numbers generally. They're different numbers. If the vector field is conservative, okay, special extra condition, then the integrals are equal. Okay, so generally speaking, if you start at a point, you end at a certain point, the path you travel along, generally speaking, matters, right? So generally, with different paths, your two integrals are going to give you different numbers. But if the vector field that you're integrating happens to be conservative, then it doesn't matter what path you take, right? So restated, maybe we can write a version of this where we don't have to mention conservative vector field. So then we won't mention a vector field directly. Instead, restated, the integral over C1 of gradient of lowercase f dot dr with an arrow equals integral C2 gradient of f dot dr. So here, no need to make mention of conservative vector field, because if it's the gradient of a scalar field, then what you have is a conservative vector field. So restated, this equals this if C1 and C2 have the same initial point and the same terminal point or final point. So there's still requirements, right? It doesn't matter what path you take when you're, as long as the two paths start at the same place and end at the same place. Okay, so to again say things differently, so here's one way to state things. Here's a second way to state things. To bring back the language of a vector field again, because this one's trying to ignore talking about vector fields, but instead talking about gradients, which, I mean, the gradient is itself a type of vector field. But just to bring it back, we'll say it this way. So if C1 and C2 have the same starting point, or initial point, okay, same initial point, and same terminal point, and if the vector field, capital F, is conservative. This is key. You got to have this. Then the integral over C1 of f dot dr is equal to the integral over C2 of f dot dr. Okay. So we've said basically the same thing 3 times in some sense. The fact that this occurs any of the three ways it's been stated, this is called path independence. So I don't want you to think of path independence as having some formal terminology, but this is a phenomenon that is occurring. Let's say there's a certain pattern, there's a certain behavior going on, and we just informally call this path independence. Okay, so what I'm trying to get at is, we'll just try to draw a picture. Let's say you've got a point here and a point there, and you can look at this path, or you can look at this path, or you can look at this path, or you can look at that path, or you can look at this path, or you can look at a path that, to be honest, does something like this. It just kind of is much more wiggly. Then the point is, since all these paths start at the same place and all these paths end at the same place, if f is conservative, again, key requirement, then the line integral of f over any of these paths, now keep in mind all these paths start at the same point and end at the same point, over any of these paths give the same number. Alright, so if capital F is conservative, so if you have a conservative vector field, then you have path independence. Okay, if then. Now here's the funny thing. It turns out also, if you always, just more a factoid, if you always have path independence, then it turns out that f is conservative. So it goes both ways, actually. Alright, so theorem. Suppose vector field f is a continuous vector field on a region capital D. So continuous vector field, we haven't defined this carefully, but I hope it seems to make sense, just in the sense of, like, if you move just a little over, you just change your input a little bit, the new arrow that you're looking at as output isn't drastically different. So it can't, like, be pointing in the complete opposite direction. It can't have, like, a wildly different magnitude. It's got to continuously change. It's got to gradually change from one location to the next. So then if integral over c of f dot dr is independent of path, in D, then f is conservative. So this is just a bit more of a factoid. I think the key thing that we'll use a lot more is f is rather the other direction, that if f is conservative, then you have path independence. Okay, and again, just to make sure, it's just more, the theorem itself, I don't think we're really going to ever really apply. This is more just an excuse to remind you what f is conservative really means, because it's come up multiple times. So in other words, what is, if f is conservative? This just means that there is, or there exists, a function lowercase f such that capital F arrow is equal to gradient of lowercase f. Okay, let's make sure that an earlier idea was made clear by having you articulate what's going on here, an interactive question, and ask the following. Just to set the stage, there are two methods. We've learned two methods to find the line integral of a vector field. So I think it'll help if you name them to answer this question. When does each method apply? Alright, so then next time, what we're going to do is we'll talk about detecting path independence. Among one topic, and perhaps a topic you sort of feel like you're chomping at the bit for based on the hint given in an earlier problem. We'll also talk about finding a lowercase f such that the given vector field is equal to the gradient of lowercase f. That is finding a potential function. Yeah, so it's one thing when you're provided a vector field and maybe it's conservative, but if so, you're going to need that lowercase f in order to apply the fundamental theorem of line integrals. So how do you get that lowercase f? That's what we'll talk about next time.